Hey guys, today I'm going to talk about the overview of nuclear chemistry. When you think about nuclear chemistry, what you need to think about is the nucleus of an atom. That means that we care about the protons and the neutrons. We don't care about the electrons. So yeah, let's talk about the protons and neutrons a little bit. They're always in the nucleus. We're going to go over some of your vocab words in terms of what is a strong force, what's holding it together, and that sort of thing here in a minute. Um, but first thing, look on your periodic table. And what you should notice is the atomic number. Look at carbon, atomic number is 6, nitrogen, atomic number 7, oxygen, atomic number 8. And what that means is that is the number of protons in the atom. So make sure you know that that is not the number of neutrons. When we get downstairs and you watch the other video, you'll see how we determine the number of neutrons, but that is the number of protons on the periodic table. Okay? So next, turn to the definitions on your WebQuest. Turn to that page. I'm going to go through all the definitions just really quickly so you fully understand it. And feel free around the room, ask me questions about any of these definitions or what they really mean. And I'd love to talk more about it. So first, couple definitions go together. Nucleon and nuclide, or nuclide. Okay, I call it nuclide. So feel free to say it however you would like. A nucleon is anything that's inside the nucleus, any particle. So those are going to be your protons and neutrons. Those are the nucleons. The nuclide is actually the nucleus. And the reason why they say nuclide or nuclide is because when you have that plural, nucleides. When you say nucleus is plural, nucleuses. It sounds funny. That's really the only reason. Okay, so it just has to do with the English or the Latin of it. Realistically, that's why we call it nuclide. So, nucleon, any of the particles in the nucleus. Nuclide, just the nucleus itself, or more than one nucleus. Okay. Next thing is the strong force. The strong force is the force that holds together the nucleus. Think about what's in the nucleus. Proton, neutron, proton, neutron, proton, neutron. Protons don't want to be together. That's because they, positive charge, they don't want to go together. Positive and negative attract, two positives repel. So there has to be something that holds them together. And what that's called is the strong force. Okay? Strong force actually is a fundamental force of nature. There's 4 of them. Don't know if you guys have studied the Big Bang Theory or not, but there's 4 fundamental forces, and the strong force is one of the original fundamental forces. And with that said, it's a lot stronger than the other forces. It's substantially stronger than gravity. Gravity is very, very weak comparatively to the strong force. Because gravity can't hold 2 things together. Gravity is essentially a force of different bodies or different things of mass. And those have some sort of force or attraction between them due to their size. That's what gravity is. So as I said, the strong force, very, very strong, holds together the nucleus, hard to separate. Okay, since it's hard to separate, we're going to talk about what that means. A lot of energy will be released, which is the purpose of hydrogen bombs, fission bombs, anything like that. Lots of energy is released. So next vocab word is mass defect. This deals with energy as well. Einstein's equation, E equals mc squared, is essentially a relationship between energy, which is your binding energy, and mass defect. Okay, and what I mean by that is the binding energy and energy still holding the particles together, and the mass defect, which is the difference in mass between the particles together and the particles separate. So that means that there is energy just because these particles are together. So those particles being together, there's some sort of energy. If you separate them, they actually lose some energy. So if we think about breaking apart a nucleus, energy is released from that, which is what makes it so harmful. If you have enough of those they're not bonds, I apologize. If you have enough of those particles breaking apart and forming new nuclei, then that's going to release a lot of energy, which is the mass defect. So E equals mc squared, probably heard it, Einstein, a long, long time ago. That's kind of what it stands for. It dealt with the nucleus of an atom. Next word is radioactivity. Radioactivity is essentially anything that decays or breaks apart to form something else. That's radioactivity. So you've probably seen that a lot. Even if we think about human body, we can see how old something is due to it breaking down over many, many years. It's going through a certain decays. Most of the time, that's very, very slowly. So yes, a lot of those beta particles, gamma particles are being given off, but at such a slow rate, it doesn't really cause any harm. It's when radioactive materials that go through those very quickly, and those are called half-lives. But if they have a small half-life, they're going to break apart and turn into something new very rapidly, and going through these decay reactions that we're going to show you downstairs here in a bit. So that's radioactivity. We will talk about that though. So there's three different essentially particles that we're going to be talking about. Alpha particle is not on here. That is a helium atom. It's 4,2 helium. So 4 being the mass number of protons and neutrons added together. So 2 plus 2 is 4. 2 being the number of protons, and it's helium. That's a helium atom. So that would be alpha particle. I'll show you the symbol downstairs. Beta is going to be essentially the electron. We'll also do a positron emission. So you also get neutrinos, antineutrinos through that. You're going to get all that information. That's the focus of the next one. Gamma ray is essentially a lot of energy given off. Gamma rays are very, very dangerous because of the amount of energy that is released. So yeah. Definition of a chain reaction and nuclear fission. Those will go together. Nuclear fission is the breaking apart of a nucleus. If you have something heavy like uranium, okay, 235 uranium, which is element number 92, if you're trying to find your periodic table at the very bottom in that block. That's going to break apart into other things. When that breaks apart, that's a fission reaction. That's going to break it apart into new nuclei. That's going to be a chain reaction. As soon as that happens, neutrons are going to essentially split, not split up individually, but they're going to come off of the atom, and then they're going to hit other particles, or other particles of that uranium, and then that's going to split again. That's a chain reaction. So, fusion is the complete opposite. If we're going down just a little bit, fusion is where you are putting atoms together. So you're putting the nucleus together. The easiest example of this would be hydrogen and hydrogen. Take one proton and take another proton. Okay, let's add a neutron to each. So 2 1 hydrogen and 2 1 hydrogen. Put it together through a fusion reaction, and you get helium, 4,2 helium. That's the easiest type fusion that we can really talk about. If you look at the sun, that's just constant fusion. Lots and lots of energy given off, which is why we see it. We see all that energy given off through photons. What else do we have? Critical mass. Critical mass is the minimum amount of material that we need in order for that chain reaction to happen. Because what happens is, if this is my atom and it gives off this neutron, there has to be something hit by that neutron for that to explode. Okay, for that to be energized enough to break apart again. If this is my atom that's going through and emitting this neutron, and it misses this atom, well, then nothing happened. Nothing happened. It's not a chain reaction. That's why you need a critical mass, a small or enough matter for that to continue. It has to hit somewhere. Half-life is the last term that we'll talk about. Half-life is the time it takes for a half of a sample to decay. In the third video, you're going to see what we're talking about when we talk about half-life, but it's the amount of time it takes for a sample to decay. Okay? So, hope you enjoy the next couple of videos, and like I said, let me know if you have any questions throughout this.